Hello, guys. Welcome to Stars with me, your very own Summit, or you can call me, or another name. Another name that I came up with is Science. And as you know, my full name is Saison Koda, so I guess that kind of makes sense. So basically, the first thing you do is you have this big, cloud of stars. This big kind of cloud filled with like stuff like dust and gases and then all that stuff here, as you know, is everything is acted upon by the force of gravity. So that's over time that becomes over time this nebula, as they call it, becomes denser and denser and gets pushed together. And finally, they get pushed together so hard that the molecules get pushed together that you have a new force that's opposing this gravity. And this force is created by a fusion reaction. And it forms the core. And this overcomes it, and after this stage, it's not called a nebula anymore. Let's zoom out. Not called a nebula anymore. It becomes a protostar. Becomes a protostar or a baby star. It kind of becomes a baby protostar. And then over time, I'm going to draw the core here. So this red part is the core. And over time, the core overcomes, and the core makes the star grow bigger as it tries to balances with the inward force of gravity. And then you have your actual main sequence star, which is what our sun is right now. And this is like an adult star. And then the different colors of stars depend on their temperature. So our sun is yellow, so it is yellow, so it's kind of like this. It's kind of like yellow. So I'm just gonna make this look like our sun. Yeah, so let's say that this is the early main sequence star sun. So something to know about this is if you were to talk, let's say if you had this red material over here, would you consider it hotter than this blue material? You don't know the actual temperature. Would you consider it hotter or colder than the blue material? Obviously, you would pick the red material. But in space, it's different. So actually, probably if you're an astronomer and if you're a good astronomer, you probably know this. This blue star over here, more like a blue star. This blue star over here is actually hotter than this red star. Actually hotter than this red star over here. And the sun, this yellow one is kind of in the middle of temperatures. Just remember, this is cool and this is hot. So that's kind of amazing. And actually it also applies here on Earth. If you've seen in fires, let me draw a good picture of a fire over here. Good picture of a fire. Put some logs. I'm not very good at drawing campfires, so mind my artwork, please. This is a campfire, a very bad campfire. And at the base, you'll see these blue flames, maybe. Base, you'll see these blue flames. And the rest will be just burning hot fire. And also, I don't know how to draw fire, so that's that. And then you have burning hot fire. See, so at the blue part, it's actually hotter and the red part. So this does also apply on Earth, but you just don't see it being applied that much because normally you think of things that are, it's because you need to go to a certain temperature to achieve the blue. That's why. So next we have what happens to a star after. Okay, so most of you probably know that hydrogen is the reason for nuclear fusion happening in the core of stars. So I'm just going to put the core back in for our sun. So what happens if the core runs out of hydrogen? Well, in the core, the more hydrogen burns. So if the star wants to survive, it has to burn elements. It has to fuse elements like helium into more heavier elements like carbon or nitrogen or oxygen even. But they can only fuse and as the elements keep getting heavier and heavier, the outer layers of the star are pushed out, and then they become supergiants. And they become red. A lot of them become red supergiants. Our sun will probably become a red supergiant. A red giant. Supergiants are when really massive stars go into this phase. So then you have these red. Where did my picture? You have red supergiants. Don't know why that's not loading in. Oh yeah, there's the red supergiants. And then the sun has limits. So stars can only fuse until iron or nickel. So as soon as they go past that, some stars they can go into one form. One form they can go into is they can turn into white dwarfs. they can turn into white dwarfs. It must be hard for you, which is basically the core of a dying star. The outline with black so you can see it better. With black, so I'm just outlined it with black. So this is what's called a white. This is a white dwarf, and this is what's going to happen to the sun because it's not big enough to go into a supernova. Comes a white dwarf, and this is a dying core. It's the dying core of a star, and soon it'll become a brown dwarf, which means an almost dead star, and then it'll become a black dwarf. And also, if the star is big enough, like, I'm not sure exactly, but if the star is big enough, it can explode into a supernova. Which is when the inward pressure of gravity forces the core inside, and then the core releases this powerful burst of energy and gets destroyed. And then this supernova, it scatters all its elements across interstellar space. And then it's this where, and if you're ever wondering how gold came to our planet, this is why. The supernova, so the force of the supernova is so strong that electrons and protons get fused together. They get fused together, and they turn into neutrons, which have no charge. And neutrons are swallowed easily by the ion group elements. So the elements keep getting heavier and heavier, and the sun and these supernovas can make elements up to uranium. And then they get scattered all across space, so that's how we got gold. When the ancient stars exploded, we had gold spread across the universe, and in young Earth, the gold was embedded in the veins of young Earth, and that's how we got gold. Although diamonds... Okay. Hello. Good. So I'm back after 2 hours, actually, because, for you it's just a second. So, when I was discussing about how gold is embedded in veins of Earth, and also this is one way the supernova can happen that way. The other way a supernova can happen is to kind of move over for this one and select. Yeah. So I'm not next, but like another process that can happen in even more massive stars is they can turn into black holes. It can also turn into black holes. Black hole is something that we don't completely understand yet. So they're caused by this thing in the center called a singularity, and we will explain later what that is. It's a point of infinite density. And it creates a powerful gravitational force that lets almost nothing escape. Not even light can escape a black hole. So that's another way. So in the case, so one more thing I forgot to mention. If a star collapses in the green way, I put in right here, then after this step, after this step, what will happen is you'll have a neutron star. So a neutron star is caused in a supernova. So basically, a white dwarf. So a white dwarf is created when there's these things called degeneracy pressures. So when you have a quark star, when you have a white dwarf up there, there's the white dwarf all the way up here. When you have the white, like for example, the white dwarf up here, that's caused by electron degeneracy. That's called by the electron. I'm just gonna abbreviate dP for degeneracy pressure. That's caused by the electron dP. But the neutron star is not applicable with that. So the electron degeneracy pressure does not apply. The electron dP does not apply because a neutron star overcomes the electron dP. So then it's stopped by the next level, the neutron dP. The neutron degeneracy pressure, it's stopped by the neutron dP. And there's actually one more stage that I can go from, and also we haven't actually proved that these exist yet. This is just a theory. So these things are called quark stars, and they're hypothetical, which means it's not actually been proven that they exist. But if something overcomes the neutron degeneracy pressure and does not become a black hole, there's one more pressure to go, and it's called the quark dP. Again, dP stands for degeneracy pressure, so it's the quark dP. So if it surpasses the neutron dP, it'll go to the quark dP. And just one big science lesson: neutrons and protons are made up of these. So each proton and neutron is made up of 3 quarks. And okay, so this proton over here, it has 2 up quarks and 1 down quark. And this neutron reader has 2 down quarks and 1 up quark. And there are actually 6 different types of quarks. These are the most common ones. There's strange quarks, there's charm quarks, there's many others. So we don't know what happens. We've never observed quark stars before. So this is really just hypothetical. Maybe we will observe them in the future, we don't know. We don't know. And neither do I. Let me just zoom out so you can see the life cycle of the stars. Okay, so let me kind of zoom out for you so you can see this. Okay, so the process starts from a nebula, then it's a protostar, then you have the main sequence star, and it turns into a red giant. Then you can go 3 ways: a supernova, which also leads to a black hole. You have supernova, which can lead to a neutron star or a black hole, or it'll just shrink into a white dwarf. Then, if it goes to the supernova, it becomes a neutron star because of the neutron degeneracy pressure. And then there's a theoretical quark star. That'll happen if it can overcome the neutron degeneracy pressure, and then the quark degeneracy pressure will act on it. So that's basically the end. Bye. And also, turns out,